Hey everyone, and welcome. We're about to tackle a topic that might sound super technical at first, transient heat conduction. But what if I told you that by the end of this, you'll be able to look at pretty much any everyday object and figure out exactly how it heats up over time? We're going to walk through a real-world problem step by step. So let's jump right in.
Think about it. You've probably done this 100 times without ever thinking about the physics behind it. You plug in an iron, you wait a bit. But how long is that wait really? And how could we possibly predict it? Well, this is the perfect example of transient heat conduction, where temperatures are changing over time. Today, we're going to put on our engineering hats and figure out the answer to that exact question.
All right, so let's frame this just like you'd see it in a textbook or, on an exam. We're turning a simple morning chore into a full-blown engineering challenge. Okay, here's the setup. We've got an 800-watt iron, and it has a standard aluminum base plate. It's starting out at room temperature, let's say 22 degrees Celsius, and our goal is to get it up to a nice, hot 140 degrees. So the big question is, how long is that going to take? And maybe just as importantly, can we make our lives easier and just assume the whole plate heats up at the same rate? That's a big assumption, so let's find out if it's a good one.
Now, before we even think about touching a calculator, a good engineer always maps out a strategy. I'm telling you, this is the most important part of solving any problem. It's not about memorizing formulas. It's about understanding your approach logically.
And, this is often the trickiest part, isn't it? Just staring at the problem, wondering where to start. Well, the very first step is always to simplify the messy real world into a model that we can actually work with. Okay, first things first, let's make some smart assumptions to make our lives easier. We'll say that the heating element is about 85% efficient, because in the real world, you're always going to lose some energy. We'll also assume that the properties of the aluminum, like its density, don't change as it heats up. That's a pretty safe bet for this temperature range. And finally, we'll assume heat escapes into the air evenly across the whole surface. See? These little assumptions turn a really complicated scenario into something we can actually solve.
All right, next up, we gather all our ingredients, just like a chef laying everything out before they start cooking. We've got the density and the specific heat for aluminum that basically tells us how much energy it takes to raise its temperature. We have the plate size, the heat transfer coefficient, which, just tells us how easily heat can escape into the air around it, and of course, our start and end temperatures. With everything organized like this, we're ready for the main event.
With our plan in place and all our data lined up, it's finally time to crunch some numbers. And you know what? It all starts with one really simple but powerful idea. The core of this whole thing is actually a super simple concept: the energy balance. Think of it just like a bank account. The energy you put in from the wall socket minus the energy that leaves or escapes into the air, that equals the change in the energy that's stored in the iron's base plate. And how do we see that stored energy? Well, we see it as the temperature going up. It's really that straightforward. Okay, let's break that down piece by piece. First, we need the mass of the plate. We just use its density and volume for that. Easy enough. Next, our energy in. That's the 85% of the 800 watts, which gives us 680 watts. Then we calculate the energy out. That's the heat being lost to the air. And that turns out to be about 21.2 watts. So after plugging all those numbers into our energy balance equation and doing a little bit of algebra to solve for time, we get our answer. Drumroll please, 65.1 seconds. Yeah, just over a minute for our iron to be ready to go. This is a perfect example of how a really fundamental principle can give us a super practical, real-world result.
But hold on, we're not done yet. A calculation is just a number. A real engineer always goes back to question their assumptions. This is the step that really separates the pros from the beginners.
Remember that bonus question we had at the start? We just went ahead and assumed the entire plate, all half a centimeter of it, was at the exact same temperature at all times. But think about baking a potato in the oven. The outside gets hot way before the inside does, right? So, was our assumption for the iron actually any good?
So, to check our assumption, we use this amazing little tool called the bio number. Now, it sounds kind of complicated, but trust me, it's just a simple comparison. All it does is it compares how hard it is for heat to move through the object versus how hard it is for heat to leave the object's surface. That's literally all it is.
And here's the rule of thumb you're going to want to remember for your exams. If the biot number is really small, we're talking less than zero point 0.1, it means heat flows around inside the object super easily. It's like traffic on a wide open highway. The real bottleneck is just getting the heat to leave the surface. And if that's the case, our uniform temperature assumption is totally valid. But if the biot number is large, it's like a massive traffic jam inside, and the temperature is going to be all over the place. So let's calculate it for our iron. When we plug in all the numbers for that aluminum plate, we get a biot number of 0.00034. That is way, way smaller than 0.1. So what does that tell us? It means our assumption wasn't just a good guess, it was spot on. The highway inside that metal is wide open.
So what have we really done here? We haven't just solved one problem. We've actually built a powerful, repeatable method for solving these kinds of problems. Let's wrap this all up into a battle plan you can take with you into your next class or your next exam.
Here it is, your 5-step framework. 1. State your assumptions. 2. List out all your properties and knowns. 3. Apply that powerful energy balance principle. 4. Do the math. And 5, and this is the critical one, don't forget it, always, always check your assumptions using the biot number. You follow these steps and you will nail these problems every single time.
We figured out the iron, but this framework, it applies everywhere. How long does it take for your coffee mug to cool down? Or think about a car engine. How long does it take a critical part to heat up so you can avoid failure? This is the kind of thinking that builds our entire modern world. So my question to you is, what will you analyze next?